In episode 78, titled Network Diagrams, Physical versus Logical, and High-Level versus Low-Level, the focus is on diagrams as communication tools that prevent mistakes by making intent visible. Networks fail as much from misunderstanding as from hardware faults, and diagrams are one of the few artifacts that can align engineers, auditors, and leaders on what exists and how it should behave. The exam tests diagram concepts because scenario questions often assume you can choose the right view for the problem, whether you are troubleshooting a cable path, validating segmentation, or explaining risk to executives. A diagram is not a decoration. It is a decision aid, and different diagram types answer different questions. If you present the wrong diagram to the wrong audience, you can cause confusion, delay decisions, and increase incident duration. When diagrams are accurate and versioned, they become an operational safety net during outages and maintenance because responders can trust them under pressure. When diagrams are stale or messy, they become a source of false confidence, which is worse than having no diagram at all. This episode builds clear distinctions between physical and logical diagrams and between high-level and low-level representations, so you can select and maintain diagrams as part of reliable network operations. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Physical diagrams show hardware, cabling, and locations, focusing on what equipment exists, where it sits, and how it is physically connected. A physical diagram answers questions like which switch is in which closet, which rack holds the firewall, and which fiber run connects an intermediate distribution frame to the main distribution frame. Physical diagrams often include device models, port numbers, patch panels, uplink paths, and sometimes power and environmental context because these details affect availability and troubleshooting. This view is essential during moves, adds, and changes because it guides technicians on what to plug in to what, reducing mispatching and accidental outages. The exam expects you to recognize that physical diagrams are the right tool when the problem is physical, such as diagnosing a link down event, planning redundancy paths, or confirming that circuits terminate in separate rooms. Physical diagrams also support facilities coordination because they clarify locations, access needs, and environmental dependencies that influence uptime. They are also critical for inventory and life cycle planning because they show which hardware exists and where it is deployed. When you think physical diagram, you should think where things are and how cables run, which is the foundation for many operational actions. Logical diagrams show subnets, routing, and trust boundaries, focusing on how traffic moves and where policy is enforced rather than on which exact cable is used. A logical diagram answers questions like what subnets exist, how they route to each other, where default gateways live, and which zones can communicate through firewalls and access control lists. Logical diagrams are where you express segmentation, such as separating guest networks from corporate networks, and where you show the control points that enforce trust boundaries. This view is essential for security reviews because it clarifies what is reachable from where, which is the core of network security posture. The exam expects you to recognize that logical diagrams are the right tool when the problem is about flows, policy, and architecture, such as validating that a database network is isolated or that administrative access is constrained. Logical diagrams are also valuable for explaining changes like adding a new subnet, implementing a transit hub, or introducing a new inspection point. They abstract away the physical details so the focus remains on intent and connectivity. When you think logical diagram, you should think how traffic is supposed to move and where it is controlled, which is what many design questions are really about. High-level views are typically used for executives and non-technical stakeholders because they communicate risk, scope, and major components without drowning the audience in implementation details. A high-level diagram might show major sites, core services, internet connectivity, and trust zones, with simple labels that convey what is protected and what is exposed. The goal is to support decisions about investment, risk acceptance, and priorities, such as whether to add redundancy or whether to segment a network more strictly. High level does not mean inaccurate. It means simplified, focusing on the minimum detail needed to make the decision. Low-level views are used for engineers because they support implementation and troubleshooting, including details like interface names, VLAN identifiers, routing adjacencies, and precise path dependencies. The exam tests this distinction because presenting a low-level diagram to executives is often counterproductive, while presenting a high-level diagram to engineers during a cutover can be insufficient. Low-level diagrams must be precise because engineers use them to configure and validate systems, and small errors can cause real outages. High-level diagrams must be clear because decision-makers use them to evaluate options, and unclear visuals can lead to wrong decisions or delayed approvals. When you choose the level of detail based on audience and purpose, you make diagrams effective tools rather than confusing artifacts. Selecting the diagram type based on the audience and the decision needed is the core directive because the right diagram is the one that answers the question being asked. If a leader is deciding whether to invest in a second circuit, a high-level physical or hybrid overview that shows single points of failure may be the right tool. If a security architect is deciding whether segmentation meets compliance requirements, a logical trust boundary diagram is the right tool. If an operations team is troubleshooting a link flap between an MDF and an IDF, a low-level physical diagram with port and fiber path details is the right tool. The exam expects you to make this selection intentionally rather than defaulting to one diagram style. It also expects you to understand that multiple diagrams often coexist for the same environment, each serving a different purpose, and that trying to force one diagram to answer every question leads to clutter and confusion. The diagram is a communication product, and communication is contextual. When you match diagram type to decision, you reduce misunderstandings and speed up action. Standard symbols and consistent naming reduce confusion because diagrams are shared artifacts that must be interpreted correctly by people who did not draw them. Standard symbols help readers recognize devices quickly, such as distinguishing routers, switches, firewalls, load balancers, and cloud constructs without guesswork. Consistent naming ensures that devices, sites, and networks are referenced the same way across diagrams, documentation, runbooks, and configuration, reducing translation errors during incidents. The exam tests this indirectly by emphasizing clarity and avoiding ambiguity, because ambiguous diagrams can mislead responders and cause wrong actions under pressure. Consistency also supports automation and inventory mapping because names can align with configuration management databases and monitoring systems. When a diagram uses different names than the device labels or monitoring dashboards, teams waste time correlating terms, which delays recovery. Naming conventions should be documented and applied uniformly, including how you name VLANs, subnets, and zones. When symbols and names are consistent, diagrams become reliable tools rather than one-person interpretations. A scenario where a logical diagram clarifies firewall placement and flows shows how logical views make security posture visible. In this scenario, the team is trying to determine whether a sensitive application is properly segmented and whether traffic between zones is inspected and logged. A logical diagram can show which subnets exist, where the firewall sits between trust boundaries, and which flows are allowed between the application tier, database tier, and external networks. It can also show where administrative access enters and which management networks are permitted to reach critical systems. This helps reviewers reason about whether policies align with least privilege and whether there are any unintended paths that bypass inspection. The exam expects you to use logical diagrams for this type of question because firewall placement is fundamentally about trust boundaries and traffic flows, not about cable paths. A physical diagram might show where the firewall device is installed, but it would not necessarily clarify which subnets pass through it and which do not. The logical diagram makes reachability explicit, which is the core of security review. When you use a logical diagram to clarify flows, you reduce the chance of relying on assumptions about where traffic goes. Mixing physical and logical details in one messy view is a common pitfall because it creates a diagram that is too detailed for high-level decisions and too abstract for implementation, leaving it useful for no one. When a diagram attempts to show rack locations, port numbers, IP subnets, routing policy, and trust zones all at once, it becomes visually crowded and readers cannot find the information they need. This also increases the chance of errors because the author must keep many different data types synchronized in one artifact. The exam tests this pitfall because it highlights the importance of choosing the right abstraction level and avoiding diagrams that confuse rather than clarify. A messy, mixed diagram also becomes harder to maintain, increasing the likelihood that it becomes stale. The better approach is to maintain separate diagrams for separate purposes, such as a physical layout view and a logical flow view, with consistent naming between them. When you separate concerns, each diagram remains readable and maintainable. A diagram that tries to do everything usually fails at its primary job, which is clear communication. Stale diagrams are another pitfall because they mislead responders during incidents and can cause wrong actions that extend downtime. During an outage, teams rely on trusted artifacts to decide what to check, what to restart, and what to reroute, and a stale diagram can send them to the wrong device or make them believe redundancy exists when it does not. Stale diagrams also undermine audits and change reviews because they no longer reflect actual architecture, creating gaps between what is claimed and what is true. The exam tests this because operational reliability depends on documentation accuracy, and diagrams are a core part of that documentation. Staleness often happens when diagrams are treated as one-time deliverables rather than living artifacts tied to change control. The result is that diagrams slowly diverge from reality as ports are repatched, subnets are added, and new devices are installed. When a crisis hits, the team discovers the diagram is wrong, and time is lost verifying basics instead of solving the problem. Keeping diagrams current is therefore a resilience practice, not administrative overhead. Quick wins include versioning diagrams and storing them with change control, so updates are tracked, reviewed, and aligned with actual deployments. Versioning means each diagram has a clear revision identifier and date, allowing teams to confirm they are looking at the current view. Storing diagrams with change control means diagrams are updated as part of the change process, with review and approval similar to configuration changes. This reduces drift because diagram updates become a required step rather than an optional afterthought. The exam rewards this kind of governance because it reflects mature operations and reduces incident risk. Versioning also supports rollback and post-change validation because you can compare before and after states and confirm what changed. When diagrams are treated like code, they remain reliable and auditable, which supports both operations and compliance. Quick wins also include having a clear storage location that responders can access during incidents, avoiding the diagram on someone's laptop failure mode. When diagrams are versioned and controlled, they stay useful. Operationally, tying diagrams to configuration management databases and runbooks increases their value because it connects visual understanding to actionable procedures and accurate inventory. A configuration management database provides authoritative records of devices, interfaces, and relationships, and linking diagrams to those records helps keep diagrams current and reduces manual duplication. Runbooks describe how to respond to incidents and perform maintenance, and diagrams provide the visual context that makes runbooks easier to execute correctly. For example, a runbook for circuit failover is more reliable when it references a diagram that shows the circuit path and the devices involved. The exam expects you to view diagrams as part of a documentation ecosystem rather than as standalone pictures, because reliable operations require cross-referenced artifacts. This integration also supports onboarding and training because new staff can learn architecture through diagrams and then follow runbooks to perform tasks. It also supports audits because you can show that architecture intent, inventory records, and operational procedures are aligned. When diagrams are connected to systems of record, they are less likely to become stale and more likely to be trusted under pressure. A useful memory anchor is physical shows where, logical shows how traffic moves, because it captures the essential difference that drives correct diagram selection. Physical shows where devices are located and how they are physically connected, which supports cabling, facilities coordination, and physical troubleshooting. Logical shows how traffic moves between subnets and trust zones and where policy is enforced, which supports security design and routing validation. This anchor helps you answer exam questions that ask which diagram type is appropriate because you can map the question to where or how. It also helps you avoid mixing details because you can decide which view to produce based on the primary question. When you apply the anchor, you create diagrams that communicate clearly rather than diagrams that attempt to be universal. It also helps you teach others because the distinction is simple and memorable. When you can explain this anchor, you can explain diagram purpose effectively. To apply the concept, imagine being asked to choose which diagram answers a given question and align the question to the needed information. If the question is, which closet hosts the firewall and which patch panel connects to the provider circuit, the physical diagram is the right tool because the answer is about location and cabling. If the question is, which networks can reach the database and where is traffic inspected, the logical diagram is the right tool because the answer is about routing and trust boundaries. If the question is, can leadership see where our single points of failure are, a high-level diagram is appropriate because it communicates risk without overwhelming detail. If the question is, what interface and VLAN should this uplink carry, a low-level diagram is appropriate because it supports implementation precision. The exam expects you to select the view that supports the decision rather than to default to the diagram you like. It also expects you to recognize that you may need more than one diagram to answer different questions about the same environment. When you match question to diagram type, you prevent miscommunication and reduce error. To close episode 78, titled Network Diagrams, Physical versus Logical and High-Level versus Low-Level, The core value is that diagrams prevent mistakes by making architecture visible to the right audience at the right level of detail. Physical diagrams show hardware, cabling, and locations, while logical diagrams show subnets, routing, and trust boundaries, and each answers different classes of questions. High-level diagrams support executive decisions and risk communication, while low-level diagrams support engineering implementation and troubleshooting precision. Selecting diagram type based on audience and decision keeps diagrams usable and prevents clutter that confuses rather than clarifies. Standard symbols and consistent naming reduce ambiguity and align diagrams with monitoring and configuration records. Logical diagrams are especially useful for clarifying firewall placement and traffic flows, while mixing physical and logical details in one view often creates unreadable artifacts. Stale diagrams are dangerous because they mislead responders during incidents, and versioning and storing diagrams with change control keeps them accurate and auditable. Tying diagrams to configuration management databases and runbooks connects visuals to systems of record and operational procedures. Your rehearsal assignment is a diagram description exercise where you describe one physical diagram and one logical diagram for the same site in words, stating what each includes and what question it answers, because that exercise demonstrates diagram selection reasoning the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.